Okie dokie little smokies, here we go. So this is all coming from 5.6. This is all about complex numbers. So remember how I said we could not take the square root of negative numbers. Well, now we're going to be able to start to do that. So this is what we call complex numbers. Whenever you have the square root of a negative number, basically what that means is when you have the square root of a negative number, and it doesn't matter what number. Here I've got 1, but it doesn't matter what number it is. The negative will pop out and become this letter I, which we call an imaginary number. So whenever you have the square root of a negative number, the I is going to pop out to represent that negative square root. In fact, I really represents the square root of -1, which you're going to see a lot more of that coming up here in a couple minutes. But now we know that we can take the square root of negative numbers, and what it creates is the complex number system for us. So this is a new numbering system that gets added on to our real numbering system to make it more complete. And so what you see over here is what a complex number really looks like. A complex number is made up of two pieces. It's made up of the real part, and it is made up of the imaginary part, where in your assignment they'll be asking you about some of the real parts and the imaginary parts when you're trying to answer questions. The real part is like our normal system that we've been dealing with. Everything that we've dealt with up to 5.6 has all been the real numbers. In fact, every real number that we've been dealing with is really an imaginary number or a complex number in disguise. Just the complex part, the imaginary part, is a 0 I, because 0 times I is just 0. So all real numbers can be converted into imaginary numbers. Just tack on plus 0i. In this section, you'll actually be dealing with both of these guys, the real and the imaginary part, which you'll see coming up in the second video to 5.6. So you'll see a lot of the real part and the imaginary part. So we're going to talk more about that later on. But right now, this video, it's all about the complex numbers, more specifically, the imaginary part. So we're going to be talking about this guy right over here in this video. Okay? But this is what the complex numbers are. So first, let's talk about a pattern, because there's going to be questions where they're going to want to know what is this simplified down. So what happens when I have I to a power? I need to know what it simplifies down to. And that's what this pattern is going to show us. Okay? So there's some things I want you to see first. So walking through this, what does I really represent? Well, that's just the square root of -1, and we already know that the square root of -1 is just I. So anytime you have I to the first power, we just call it I. Now, I squared is important to us because you're going to see it pop up a lot coming up pretty soon. So I squared, well, what does that really look like? Well, that means it's a negative square root of 1 times a negative square root of 1. Okay? So when you multiply these two, being that they are the same square root, what's going to happen is the -1 will pop out. So I squared really represents -1, because the square roots will just cancel each other out. Okay? Remember, we talked about that. When you have the same square roots multiplying each other, they cancel each other out. Down here, I cubed really looks like the square root of -1 times the square root of -1 times the square root of -1. Well, we just talked about this a moment ago, where these two guys right here, we know they form -1. And then we just have left the square root of -1. Well, if we put all this back together, don't we know what the square root of -1 is? Absolutely. It's -1i. Or in other words, what we call this is -I. So I to the third power represents a -I. And finally, but certainly not least, we have I to the fourth power. What does that look like? -1 times the square root of a -1 times the square root of a -1 times the square root of a -1. But again, we know some things. We know that these two become a -1. Oh, but so will these two. So you have two -1s being multiplied, which gives us a +1. So I to the fourth is really a +1. And that's the pattern you're going to see and the one that we need to know. I to the first is I to the second is -1, I to the third is -I, and I to the fourth is 1. And what's going to happen is this pattern is going to repeat. Let me show you. I to the fifth, it's really made up of I to the fourth times an I. Well, don't we know what I to the fourth is? It's 1. And 1 times I is just I. Notice that's the same thing that we had up here for I. I to the sixth, well, that's made up of I to the fourth times I to the second. Well, we know what I to the fourth is. It's 1. We know what I to the second is. It's -1. So in the end, we get -1, which is what I squared was. Notice I to the fifth was I to the sixth was -1. Any guesses as to what the next guy is going to be? You bet. This guy is going to end up being -I. And I to the eighth will end up being a +1. Because again, I to the seventh is made up of I to the fourth times I to the third, which we know I to the fourth is 1. We know I to the third is -I, which gives you -I. And the same thing happens down on I to the eighth. It's just made up of 2 I to the fourths. I to the fourth, I to the fourth, which is just 1 times 1, which is 1. So notice that my pattern starts with I, then goes to -1, then goes to -I, and then goes to 1. And then when you look right down here, when we start with I to the fifth, it goes I, then -1, then -I, then 1. It's the same pattern again. So I want to show you a little trick to this, that whenever you have an exponent, some I to some random power, and you want to simplify this down, here's how you can do this really, really quickly without having to write out a lot of I's, like what I did up here. So, here's a trick. Take the exponent and divide it by 4. Whatever the power on the I is, take the exponent and divide it by 4. Because the reason why we're dividing by 4, because there are only 4 options. I, -1, -I, and 1. So we divide it by 4. And you're going to end up with some number with maybe a decimal. And it's the decimal that we care about. If your decimal, when you divide, is 0.25, your answer will be I. If when you divide those out and your decimal is 0.5, your answer will be -1. When you divide and you get a decimal of 0.75, your answer will be -I. And last but not least, when you divide and you have no decimal, it's just a number, no decimal, your answer is 1. So that's how we can use our exponent of whatever I is divided by 4, and that's going to tell you what your end result is. It'll either be I, which represents a 0.25, -1, which represents a 0.5, or -I, which represents 0.75, or just 1, because there's no decimal. So let's take a look at some examples. So I to the 11th. So what I just said was take that exponent, divide it by 4. And if you divide this guy by 4, you end up with 2.75. So since my decimal is 0.75, that means my answer to this guy is -I. Really easy. 0.75 is -I, what I just told you. 72, you take 72, divide it by 4, and you get 18. Since there is no decimal, my answer to this is just 1. Try the next two. Go ahead, pause the video, give them a shot. All right, so I to the 36th takes 36 divided by 4. You end up with 9. So that means I to the 36th simplifies down to the number 1. Now the next guy you got to be careful on because it has a negative power. Remember we talked about negative powers back in 5.2? No. Yeah, 5.2, where we talked about rational exponents and things like that. A negative power, guys, all it does is move. And so right now this is in the numerator. So where it's going to go is into the denominator because negative exponents move. That's all they do. It just picks it up and moves. If that was in the denominator, I would have moved it to the numerator. Okay, so now you can actually figure this guy out. So that's the one little trick you had to do before. You had to realize that this little negative exponent was picking you up and moving you because that's what negative exponents do. They move. So now you can deal with everything. So you've got 16 divided by 4, which is 4. So that means this I to the 16th in the denominator becomes the number 1 because there's no decimal. So 1 over 1 just reduces down to 1. There's your answer. Nice and easy. All right. So we talked a little bit about I, its powers, its patterns. So let's jump into actually dealing with some radicals. So now it's going to be kind of like what we did all the way back from 5.1 to 5.3 and 5.4, where we're going to learn how to add, subtract, multiply, divide, all that stuff. Okay? So right here we have a radical, and they're all negative. So the thing that you need to understand when you're dealing with this is we're going to take care of the negative first. Make the I pop out first, and then go back to what we were doing before. Because once the I is outside, that means your number under the radical will now be positive, and you just apply the same principles that we have been using in 5.1, 5.3, and 5.4. So this guy, the I is going to pop out, and that's going to leave us with the square root of 36. And now, you just kick out the answer. We know what the square root of 36 is, and it's 6. And when we write up our answer, we always put the number in front of the I. So it'd be 6I. Normally we don't write I6. Okay? So we like to put the number in front of the I. So 6I. And then we just do the same thing on the rest of the stuff. Again, square root of negative 20. Let the I pop out. So I pops out. That gives us the square root of 20. Now you go to your calculator, you try to run the square root of 20, it doesn't work. So now you just play good child, bad child, okay? Or do your tree diagram. And when you break this down, the square root of 20 becomes 2 square roots of 5. So the 2 will go with the I in front because that's the number that those are the guys that are outside. So you got 2I, and then the square root of 5 will follow the I. So kind of an order of making your answer. You always have your guys that escape, the guys that are on the outside. Then you put your I, and then it's your square root that comes after the I. So that's kind of the order of writing this thing out and how it will like it in your assignment. You want your number that pops out, all those that escape in front of the I, and then after the I is your bad children, the guys that are left inside your radical. And then certainly last but not least down here, the square root of negative 7. So let the I pop out, and then focus in on the square root of 7. Does the square root of 7 break down? No. So that's your answer right there. I square root of 7. Done. See? Just let the I pop out. Be done with the I. Make your radical positive, and you just follow the same rules that we did before. Alright, so let's talk about a little bit of multiplying and dividing. So this page I got multiplying. On the next page I'll have the dividing. Again, Work with these as positive roots. Let the i's pop out. So the I will pop out of the square root of 2, or negative 2. And the I will pop out of the square root of negative 5. And then now we can deal with everything. Remember, numbers multiply numbers, radicals multiply radicals. So my i's will act as numbers. What's I times I? That's I squared, which we'll talk about soon enough. And then let your radicals multiply your radicals. So the square root of 2 will multiply the square root of 5 and become the square root of 10. See, it works the same way as what we did before. Numbers multiplying numbers, radicals multiplying radicals. So now you worry about doing all your simplifying. Can the square root of 10 break down? No. But I squared, we do know what I squared is, and we have to take care of that. Remember back a moment ago, we said that I squared represented negative 1. And then you just tack on the square root of 10 because it didn't break down. So there's your answer. Negative 1 square root of 10. Or you could just call it negative square root of 10. You don't have to draw the 1 in there. Okay? The rest of these are going to work the same way. Okay? Let the I pop out. Then you got the square root of 3 times I square root of 6. Then go ahead and do your multiplying. The i's times the i's become I squared. The square root of 3 times the 6 becomes 18. And then now you start to simplify. So your square root of 18, does it break down? Absolutely. Does break down. You can do your tree diagram. You can do your good child, bad child. So that becomes the square root of 18 becomes 3. And then you have a square root of 2. Because it breaks down to 9 as the good child and 2 as the bad child. And then that I squared, we know what happens to that. That becomes negative 1, which makes the 3 a negative. So there's your answer. Negative 3 square roots of 2. And then last but not least, we got the square root of 7 times the square root of, or negative square root of, square root of negative 7 times the square root of negative 7. So again, the I pops out. Square root of 7. The I pops out. Square root of 7. So that gives you I times I, which is I squared. Square root of 7 times square root of 7 just becomes 7. Remember, you're multiplying the same radicals. So the number just pops out. So in the end, we do some simplifying, and we know that I squared becomes negative 1. And negative 1 times 7 is negative 7. Okay? Just follow those same steps that we did before. Numbers multiply numbers, radicals multiply radicals. But before you do that, just let the I pop out front. So I've got 3 more examples here of dividing. So let's talk about those. So in here, remember in dividing, we always do the operation first, and then we worry about simplifying. So remember, sometimes it's better to put them back together. Sometimes it doesn't help putting them back together. So, a lot of this is up to you on how you want to work things. Okay? So, again, if you have negative square roots, just let the variable pop out. So that's I with the square root of 4 over I with the square root of 16. What's going to happen to your i's? You're correct. The i's will cancel out. So really, all we're left with is the square root of 4 over the square root of 16. Something that we have handled before. And we know what the square root of 4 is. We know what the square root of 16 is. Square root of 4 is 2. Square root of 16 is 4. Which reduces down to 1/2. And there you go. See? Nothing crazy with a negative square root. Just i's pop out. So, now, here, we got the I popping out. Square root of 45 stays. We got an I popping out. Square root of 80 stays. And again, the i's are going to cancel out, which leaves us with 45 and the 80. And I'm going to go ahead and put these back together, because if I tried to take the square root of those as individuals right now, the square root of 45 doesn't work. The square root of 80 doesn't work. But if I put them back together, they actually reduce to something that's pretty nice. They reduce to the square root of 9 over 16. And now's a good time to separate them out because we know what the square root of 9 is, and we know what the square root of 16 is. So this becomes 3/4. Okay? So again, sometimes it helps to put them back together. Sometimes it doesn't. It all depends upon what you've got. Like the next case, putting them back together will not, really give us anything advantageous. So again, over in here, let's take out the I, gives us the square root of 3. Let's take out the I, gives us the square root of 7. If I try to put those back together, you know that the 3 and the 7 aren't going to do anything for each other. So we're just going to keep them separate. And again, you see that the i's will cancel out. So what we're dealing with is the square root of 3 over the square root of 7. Now remember I told you about that one mathematician that doesn't like radicals in the denominator. So this is where we have to fix that. How do we fix radicals in the denominator? We rationalize. And remember in class, in order to rationalize, all we have to do is multiply by the radical that's down there. So the radical that's down there is the square root of 7. So we're going to multiply by the square root of 7. So on top, that gives us the square root of 21. On bottom, that gives us 7. Because square root of 7 times square root of 7, the number pops out. And the square root of 3 can multiply the square root of 7 because they're both radicals, which gives you the square root of 21. And from here, can the square root of 21 reduce? No. Is there any reducing of a fraction? No. So that's your final answer. All right, let's finish up our discussion of complex numbers. Again, we're going to go back and we're going to do some more adding, subtracting, multiplying, and dividing. But this time, instead of the radicals, they're actually going to be in the complex number form. So that a plus bi that you saw. And so we're going to talk a lot about how their answers are really written up and things like that, and how to add, subtract, multiply, divide. It's going to be really, really easy, really, really quick. So, adding and subtracting. Again, it's a lot like what we did with the radicals. You're just going to combine like terms. That's it. So here we've got 3 plus 4i plus -1 plus 5i. So the 3 and the -1 get together because they're like terms. So what's 3 plus -1? That's 2. And then the 4i and the, 5i get together. And 4 plus 5 is 9i. And so you can see the real part, which is 2, and the imaginary part, which is the 9i. So there you go. 2 plus 9i. See, adding, subtracting, nothing crazy. All we're going to do is combine like terms. So just be careful of the subtracting, just like normal. You've got to watch out because remember that this little guy right here changes all of those because it's like distributing through. So really what you're looking at here is 7i minus 3 minus I. So just be careful of that. Okay? And again, all you do is combine like terms, just like what we did up above. So is anybody getting together with the -3? No. But it doesn't disappear. We still write it down. And then last but not least, is anybody getting together with the 7i? You bet, the -I. So what's 7 minus 1? Positive 6i. And that's how they'll want it written up. They will want the real part first, and then the imaginary part second. If you write it like this, it really does not like that. That's kind of incorrect, because we always want the real part first, the imaginary part second. Okay? That's that form that I was talking about to you guys before. This is how it should be written up. The real part is the -3. The imaginary part is the 6i. And again, I just got one more about subtraction. So again, just be careful, because remember this guy's coming through here and changing all those signs. So what we have is 6 plus 2i minus 12 plus I. So when you put everybody together that needs to get together, this is what you end up with. 6 minus 12 gives you -6, and 2 plus 1 gives you a positive 3i. And again, that's how it should be written up, with the -6 first as the real part, and the 3i second as the imaginary part. All right, let's talk about multiplying complex numbers. Multiplying is just like when you guys did foiling and distributing. Make sure everybody gets multiplied. Okay? So here, all we're going to do is multiply these two guys together. So 5 times 2, that's 10. And I times I is I squared. Now here, when you start getting into the multiplying and dividing, you do have to watch out for any i's of higher powers. Like in this case, we have I squared. We know what I squared is, and you need to actually change it to what it really is supposed to be, which is -1. So you got 10 times -1, which gives us -10. So that's the answer. And just so you know, if they want this as a complex number, the -10 right there, that represents the real part. If they want to know what the imaginary part is, remember I said any real number is really made up of a 0i. So if they want the full complex number, it would be -10 plus 0i. Because there is no imaginary part on -10, so that would be the 0. And vice versa. If you had an imaginary part and there was no real part, it would just be 0. Okay? I think I have something like that a little bit later on, and I'll show you. So here we go. Let's finish up. I'll give you a moment to try out the -3i, 4i one. But let's go ahead and do this 11 minus I squared. Let's talk about that guy. So 11 minus I squared. Don't take the square through the parentheses. That's bad math, and that is incorrect every time. You're not going to take the square through the parenthesis and have 11 squared minus I squared. That's wrong. What does that square really mean? And we keep talking about this in class. It means you have 2 of those parentheses. So you have 11 minus I times 11 minus I. Okay? It means you have 2 of those. So what they really want you to do, you guessed it, they want you to FOIL. So you're going to do first, outer, inner, last. So first, 11 times 11, that's 121. Outer, so 11 times -I is -11I. It's just like taking 11 times x. 11 times x is 11x. Same thing happens with the i's. Just 11 times -I is -I. And then from here, we'll do our inner. So -I times 11 is -11I. And last, -I times -I gives us a positive I squared. So go ahead and take care of the I squared. We know what that is. I squared, remember, is a -1. So I would convert that now to that. And then this is where we'll put all of our like terms together. So you can see that the 121 and the -1 get together, giving you 120. You can see that these two guys right here, the -11i, -11i, get together, give you -22i. And there's your answer. So some of these you might have to be foiling on. No worries, not that hard. You can do it. So we still got 2 others. Go ahead, pause the video, give them a shot, see what you think. All right, so right back up here, -3i times 4i. Well, -3 times 4 is -12, and I times I is I squared. And again, we keep seeing this I squared pop up. I squared is just -1, so -12 times a -1 is a positive 12. Ooh, popping around. And again, just like before when we talked about this, there's no imaginary part, so that just means that the imaginary part is 0i. It really is there, it's just 0i. And then last but not least, in the multiplying, so we're right here, all this is just a distributive problem. So you're going to take 7i times the 1, which gives you 7i. And you're going to take 7i times the 5i. Well, 7 times 5 is 35. I squared, because I times I is I squared. Go ahead, take care of your I squared, which makes the 35 now negative. And you're almost done. The 7i and the 35 don't get together, but remember, that's not how we write this up. Remember, we always put the real part first and the imaginary part second. So the negative 35 needs to come first, and then it's a plus 7i for the imaginary part. That's what they're going to be looking for. All right. So let's jump over to our last page, dividing complex numbers. All right. So in this, little different than before, but it's going to sound a lot like what we have done with something previously. Remember that I right here represents the square root of a -1. So that means we have a square root in the denominator, and we don't like that. Remember that guy says, we don't like square roots in the denominator because it's irrational, jerk face. So we need to fix that. How do we fix this? Now most of you are like, Mr. Armstrong, we'll just multiply by I. And I'm going to be like, no. This is rationalizing where we have to use conjugates. Okay, because we have addition and subtraction in the denominator. But more specifically, we actually call these complex conjugates because they're complex numbers. But they work the same way. If you have a plus bi, the complex conjugate to it is a minus bi. And vice versa. If you have a minus bi, the complex conjugate is a plus bi. So remember, whenever you have addition and subtraction down in the denominator, you need to use conjugates. In our case, this time, it's complex conjugates because they're complex numbers. So how do I get rid of 4 plus I? We're going to multiply top and bottom by 4 minus I. And that's going to take care of the radical in the denominator for us. Now, remember what I told you, because we're using conjugates in the denominator, you can do the Florida. Multiply the first, multiply the last, get to your answer. And then in the numerator, you do whatever foiling or distributing you have to do, like normal. So, in this guy, if I do my Florida method, 4 times 4 is 16. And a positive I times a negative I is a negative I squared. But we know that that really becomes 16 minus a -1, which equals 17. So that's our denominator. Now we just work on the numerator. The numerator, this is going to be FOIL. Okay? First, outer, inner, last. So 2 times 4 is 8. 2 times negative I is negative 2I. Negative I times 4 is negative 4I. And negative I times a negative I is a positive I squared. So then converting the I squared, that gives you 8 minus 2I minus 4I minus 1, because I squared is -1. And then you just put your like terms together. So 8 minus 1 is 7, and negative 2I and a negative 4I is negative 6I. And of course you'd see if there's any reducing there, but there's not. So that right there, 7 minus 6I over 17 is your final answer. If they want this written out as complex numbers, this guy right here, this final answer, really represents 2 fractions. One where it's 7 over 17, minus the other guy, which is 6 over 17I. So there you can see the real part and the complex part. All you do is you just slap 17 under both numbers and separate them out. So you can write it like the first guy, or you can write it like the second guy, depending on which one they're asking. Okay? So I got 2 more examples. Let's go ahead and do those. If you want to pause it and give them a shot, that's fine. The bottom one's a little bit easier out of everybody, but I mean, that's about as hard as division will get with complex numbers. So go ahead and give them a shot for a second. Okay, so in this guy, you need the complex conjugate. So that would be 5 plus 3i. 5 plus 3i. So in the denominator, we end up with 5 times 5, which is 25. And then we end up with negative 3i times 3i, which gives us a negative 9i squared. Which we know what happens to that. That becomes 25 plus 9, because I squared becomes negative 1, and negative 9 times negative 1 is a positive 9. Okay, and in the end, we end up with 34 in the denominator. Now to deal with the top. So again, all you're going to do on the top is distribute. So 1 times 5 is 5. 1 times 3i is a positive 3i. 2i times 5 is a positive 10i. And 2i times 3i is a positive 6i squared. But again, we know what I squared is. It's negative 1. So really in the top, we have this. 5 plus 3i plus 10i minus 6. And all you do is, again, put your like terms together. 5 minus 6 is negative 1. 3i plus 10i is a positive 13i. And is there any reducing? No. If you wanted to separate them out into the complex number standard form, it'd be negative 1 over 34 plus 13 over 34i. And then last but not least, you don't have to use a conjugate on this one, but just so you know, this 9i down here really is a complex number in disguise. Since there's no real part, there's a 0 there, plus 9i. So if you wanted to think about it like that, I guess you could use conjugates, but it's even easier to do it without the conjugate, okay? Because all you have down here is just really a square root that you got to get rid of. And it's not really, a conjugate is not needed. But, so like I said earlier, if you just have a complex or an imaginary part, there really is a real part to it, that would be 0. Just like earlier, when I had a real part, there was no imaginary part, it was 0i. So here, all we're going to do is multiply by our conjugate, or excuse me, no conjugate, multiply by our radical. Remember, when we rationalize, we just multiply by whatever the radical is that's down there. So we're just going to multiply by 9i. So in the bottom, we get 81i squared. And in the top, you get 90i. Well, we know what I squared is. That's negative 1. So the bottom number really becomes a negative 81 over 90i. And then here, there is some reducing. 90 over 81 can reduce. And it reduces to, if you divide the top and bottom by 9, 10i over 9. And the negative, I just slapped it out front. Remember, you could put the negative up top. You could put it in the denominator. But there it is. So negative 10i over 9. And again, if they wanted the real part to this, remember the real part would be 0. So what it really looks like is this. 0 minus 10 over 9i. So there's really what it looks like as a complex number. And that ends 5.6.